So uh, just bear with me. It's just a variable. So if you do see another variable, it's just the same thing. You can use happy face as a variable if you like. You just gotta define it for the audience. So let's go back to this. Consider we have cosine theta inside parentheses secant minus cosine is all equal to sine squared. So we know how to show that the easiest way to show if it exists or it is true is plug in theta like pi over 4 in that example we saw where that identity was not an identity. So that could be one case. That could be one case you could do. Um, but sometimes we can make conjectures on patterns we see. Mathematics is about patterns. Sometimes when we have a pattern, it tends to have a conjecture. So after so many end trials, it fails. So, but besides that, besides that off topic, let's go ahead and attack this problem. It says verify algebraically that the equation is an identity. That is the best way to show whether an identity is true by proving it, and then confirm graphically. We'll just talk about it. We don't need to compare graphically, right? If we know how to prove it by hand, uh, I don't think we need a calculator to help us do that. But that's okay. We'll see what they say. So, based on what we have underlined in red, what side looks more complicated? The left hand side, okay, on the equal. This is the equal side. So whenever I write LHS, I mean left hand side for the left hand side of the equal sign, right hand side for the right side. The left, obviously, right, because it has more and trig stuff in there. So it has more trig equations there. So I believe the left hand side is the more complicated looking one. So we'll start with that, which is hinted on the beginning of how to start this problem there in A. It says the left hand side looks more complicated. So we start with it and try to transform it to the right hand side. So that's why I say this section, I feel personally, it's the hardest one when we have a little bit of difficulty with some algebra because it's easy to use the reciprocal ideas identities, but when it comes to algebra, whether it was working with fractions, everybody does not like fractions. So bear with me, especially with the reciprocal identities, they deal with fractions. So bear with me. All right. So let's go ahead and start with the left hand side. The left hand side was cosine of theta, secant of theta, secant of theta minus cosine of theta. All right. Now they gave us a little hint. They say reciprocal identity. Believe I copied and about to paste all this. I can erase this. This is what we were talking about on Monday. Right? Starting fresh. All right. Starting fresh. So this should be slide 13 now. All right. So they want us to use a reciprocal identity. So I see cosine, I see cosine, I see a secant here. So based on my reciprocal identities, right, I narrowed it down to the reciprocal identities. I want to turn secant. I want to use the reciprocal the secant because, like they say in the steps, if you're stuck, you may find it helpful to rewrite all the functions in terms of sines and cosines. All right. Before step two, because I haven't been able to use any algebra yet, it looks like I need to use some of my trig identity, and then which is a reciprocal identity. So we have secant. So we have secant. So which one does it look like? Or how am I gonna rewrite secant? What is secant equal to right here? I'm gonna even help you out. Can you unmute? I mean, chat. You all right? Can you hear me? Oh, what that is. One over cosine. Yes, awesome. Thank you. Thank you. Does anybody see where we got that? Secant actually equals one over cosine because there's a relationship between them. If you have cosine, you take the reciprocal, it actually equals secant. So that's why they say rule of thumb. If you're stuck, turn everything in sines and cosines. So that's my hint here. So is this zoomed in? Yes. So I have cosine and I have a cosine. So I might as well use a reciprocal identity and turn secant into 1 over cosine. So, all right. So left hand side, we're starting. Now we're starting to manipulate. So it looks like we're on good pace. So secant actually equals, so we're using reciprocal identity. Secant actually equals 1 over cosine, 1 over cosine of theta. Excuse my data kind of looks like Pokeball sort of. Those of you who are into that Pokemon stuff, and then we have minus cosine close data. So it's looking good. It's looking good. We're a whole bunch of cosines, that's good because uh, we're gonna be able to simplify this and turn it into sine squared. So follow along. So as we move on to the next slide, we have, I do believe, two more steps that's left. So our next step with should be, um, don't have a lot of space here. Don't have a lot of space. I would like to, let me make a new slide. Okay. Why did it go in more? Right, let me make a new slide. All right, so here we have cosine of 30. So we haven't done much. Excuse my, transition to using this system, right? Online virtual teaching. So that's all we did. We did a reciprocal identity. So the next step is to distribute. Just distribute. All right. I know it took some time just to get to the second step. Right? Distribute. So here we're left with cosine of theta over cosine of theta minus cosine times cosine. Isn't that just cosine squared? Like x times x, right? X times x equals x squared, right? So if we have cosine being multiplied by another cosine, it should be minus cosine squared of theta, right? I hate this thing in the middle. I don't know how I can get rid of it. But following along, we have our equal side. We're still, left hand side trying to approach our right hand side. What do you notice about right here? Cosine over cosine. What do you think that's gonna equal to? Cosine divided by cosine. 1, right? The loneliest number. Have you heard that song before, right? So it's the same thing divided with this. We have something divided by the same thing. So we have 1 minus cosine squared of theta. All right. So I believe that's what they have on the next slide. I believe I can do that. So here we're left with 1. Oh. Before I get there, don't want to ruin the surprise. I think I moved this in the wrong place. Like this should be over here. Oh, I one minus cosine. I don't know why I had the same slide. All right, let's see. Sorry. All right. So here we have 1 minus cosine squared. So I want you to remember Pythagoras' identity. Remember sines. So I'm going to put a little star here. sine squared plus cosine squared equals 1. Remember this one? Pythagorean identity. I hope you can see now how we're about to approach sine squared. We're almost there. Look at the 1. Look. I'm trying to turn this into sine squared. That's the next step. That's what we're trying to approach. All right. So remember Pythagoras' identity. We can go back to slide 13. Pythagoras' identity is right here. Sine squared plus cosine squared is equal 1. So what we have to do is just a little manipulation between the Pythagorean identity. We want to write this in terms of sine squared. So all we have to do is subtract by cosine squared on both sides. 1 minus cosine squared. All right. So we're left with sine squared is equal to 1 minus cosine squared. All right. Hopefully you can separate this together. Hopefully you can separate together. This is a little side note because look at this. We have 1 minus cosine squared of theta. I know I didn't write no theta on the other there, on the left hand side there. But if 1 minus cosine squared equals sine squared, can I just write sine squared next? And do you see how now we approach the right hand side? All right. So again, we ended up with 1 minus cosine squared of theta. But remember, we have Pythagoras' identity. We expanded and we got 1 minus cosine. And then the Pythagoras identity allows us to rewrite 1 minus cosine squared is simply equal to sine squared of theta, which ultimately is the right hand side. So again, let me walk you through this problem. Our goal was to go from the left hand side to the right hand side. All right. First step first, we had cosine secant minus cosine. Right. First step first, as we turn secant into in terms of cosine by using the reciprocal identity. So not much. We just did the reciprocal identity right here that I have boxed and circled in. We wrote secant as 1 over cosine. So we didn't do much there. And then we distribute it, right? So right here we distribute, right? Not the prettiest picture. I need to find a way to delete this thing in the middle. The Twitter bird and all that stuff. So right here on the right side of the squiggly line here, which looks like a mountain, it says distribute. We distribute. We ended up with 1 minus cosine squared. And then from 1 minus cosine squared, we remembered our Pythagorean identity. So this is Pythagorean's identity. That's why I mentioned that one was going to come up quite a lot in this course, the Pythagorean identity. That's why I wanted you to remember that Pythagorean identity. And the same thing goes if you wanted to solve for in terms of cosine squared. You could have done that as well. So just letting you know, you could have had cosine squared is equal to 1 minus sine squared. So we're also going to do that as well. So we end up with 1 minus cosine squared after we distribute. And then from Pythagorean's identity, we're allowed to write 1 minus cosine squared as simply sine squared. And we have approached our right hand side. How was this problem? Give me an honest opinion from on a scale of 1 through 5. because these problems are hard. You can't just guess a number. Uh, three mediocre, mediocre. Yeah. So which I do agree with you because to get rid of little things in the middle. Oh, you middle click the dotted line on the bottom. I don't know. It's not letting me. There's no box. Like the whole box. Okay, like that. Okay, awesome. Thank you. Thank you for the advice. Thank you. Thank you so much. Yeah, because those uh, get a little blurry with that. All right, so it's mediocre. And it's mediocre because we need to know our reciprocal identities and our Pythagorean identities. So if you like, uh, this could be your nice little I don't want to say cheat sheet, but your nice little guide for this chapter because we'll be referring back to reciprocal identities and your Pythagorean identities. So I recommend if you have a binder, print this out or physically write it on a piece of paper and type it to your binder. So just like the unit circle, just like the unit circle. So I suggest you have those two tools to help you as you're working. And then they say you can also do it by calculator, but that defeats the purpose, right? There's no fun in that, right? So it says if you like, you simply just graph the left because there's some calculators where you can stack equations, multiple equations on the XY system, the 2D system. So simply just graph both equations, and if they coincide with each other, they overlap with each other, then basically they equal each other. So that would be an identity. So it says we graph each side of the equation to see whether the graphs coincide or overlap, right? Perfectly overlap. From the picture below, they say the graphs happen to coincide. So they say they're an identity. Can't cut my tongue. It confirms that it's an identity. But again, that's nice. That's nice to do because maybe one time, maybe you're working on a proof and you get stuck. So one way you can do to help you at least give you some, peace of mind is graph them both and see if they coincide. If they don't, uh, then it's impossible to prove it, right? Because they don't coincide the graphs, right? They don't equal each other. So I can give you a peace of mind if you're working with an identity that is not an identity. So, but I'm glad they talk about that in the textbook because technology is very integrated into our culture now. So it says in example 3, it isn't easy how to see how to change the right hand side to the left hand side. So for example, they're saying if we ended up with sine squared, it's very difficult to end up from sine squared all the way back to the left hand side, which was cosine secant minus cosine. That it's a little bit vague, right? When you start with one trig function, right? And then you're trying to work into an expanded one. So that's why they say start with the side that looks the more complicated side. So it is possible. So let me go back to that slide. The previous example we just did, they say it's easy to see how to change the right hand side. Oh, it isn't obviously. It isn't easy to see how to change the right hand side into the left hand side, but it's definitely possible. You would just have to, undo the steps that we just did right now. But that's a little bit harder, from you start off with sine squared and you got to think, okay, Pythagorean identity, change it to 1 minus cosine squared. And then you would have to think about factoring the cosine out, and it takes a little bit of work. That method's a little bit harder. So in other words, if we start with the last expression and the proof that we did, which is sine squared, that's the last part we got on our proof. In other words, if we start with the last expression in the proof and work backwards through the steps, the right hand side is easily transformed into the left hand side. So you can just simply go backwards and just look at the steps we just did, just go in reverse. But it's a little bit harder that way. So you will partly agree. So, in the textbooks, and I have, repeating each other's words. So, obviously, I would agree that sine squared, changing it to one minus cosine, factoring out a cosine, I think that would be like that would give me a few minutes and scratch my head a little bit. Some are easy, some are straightforward, some are just a trick that you need to think of, such as a reciprocal identity or an algebra move. Those are the ones that catch me sometimes. It's algebra. It's not so much the pre-cal you're having problems with. It's algebra. So a different squares method is a technique you learn in college algebra, and I was trying to prove something, and I was stuck on it for 30 minutes, and all it was a difference in squares, and I canceled my tangent out, and I was just left with like secant, and it happens to us. It happens to us. A long day, stress day, but the important part is to keep trying, and if we get stuck anywhere, we can zoom together and then discuss how what's the best way to you know start a proof, right? So, like I said, there was the three steps, the three guidelines given, but if not, we can meet together and talk about how to prove some of these identities. So, all right, the last paragraph we're on, it says, you probably might agree, however, it's more difficult to prove the identity this way. That's why it's often better to change the more complicated side of the identity into the simpler side. So I just wanted to, give us a little peace of mind. It's okay if you wanted to take out this route, take the route of starting with a complicated site. But hey, I'll go for that any day. Within the one that looks less scary, but it's going to be more challenging to get to the other side. So, in example 5, let me see what you're talking about. All right, the following example coming up. All right. So in an example coming up, it says we introduce something extra to the problem by multiplying the numerator and the denominator by a trigonometric expression. Choose so that we can simplify the results. So let's go ahead and do this. All right. A little bit of hint was given already, helped you set up the problem. But I want you to give your honest opinion right now. Based on the identity given here, we have cosine of u over 1 minus sine u is equal to secant u plus tangent u. All right. They both look a little funky, but which one would you agree is the more complicated side? I know there's a hint given to us already. They already told us, but I want your honest opinion. Some of us may, all of us think different, right? That's what makes us unique, right? That's what makes us who we are, right? And the big thing I want to mention is the one with the fraction, right? Do we tend to not like fractions? Nobody? Anybody? Honest opinion? You got to give me your honest opinion. Uh, Fractions, right? Everybody likes fractions. Nobody says anything. All right, so that's that. I mean, they're okay, but they tend to be the ones that we don't like to work on. They're friends, yeah. They're just numbers, yeah. So that's why they went ahead and chose the left hand side. So secant plus tangent, that doesn't seem that complicated. Yeah, it has two different trig expressions, a secant and a tangent, but the one on the left has cosine divided by 1 minus sine u, and generally they're more difficult. Exactly, that's a great response. Thank you there. and they can be difficult sometimes. So therefore, all right, now thank you. That gives us a perfect idea why we're starting with the left instead of the right. The right is just adding two things. It's not so difficult to add two things. I can plug in whatever u is and do secant plus tangent my calculator. Even if they were easy numbers, say like pi over 4, square root 2, over 2. Well, for tangent, at least it's going to be some ratio of square root 2 over 2. So, for example, you have some ones that you can work with. Uh, so, all right, perfect. So that's why we're starting with the left hand side. All right, let's start with the left hand side. But here they're talking about multiplying by the denominator. So here, let me go ahead and just copy and paste what's on the left hand side. Here we have cosine u. It looks like cosine u. Again, you should always put parentheses. The textbook don't. So excuse me if I don't do it, because I don't like seeing so many letters back to back to back. Like cos u or cot x, cot x. It's not all. It's all squeezed together. So it's preference. Again, it's all preference. Everybody has a style. Uh, Especially if those of you who go into like a proof based, you want to become a mathematician. Everybody has a different style of proving things. But generally, for these, this is a little bit straightforward. But sometimes people have a different trick up their sleeve. There's many ways to get to to the right hand side or the left hand side if you're clever. If you're clever enough to figure out, to work with a particular different reciprocal identities. So in this case, we're talking about we're trying to get rid of that fraction. So one good way is a conjugate in this case, because I see a one minus sign. And remember the Pythagorean's identity, cosine squared plus sine squared equals 1, correct? So remember that I have and then if I solved for cosine squared, for example, so let me do it a little bit over here. So I want you to keep this in the back of your head right now, right? This 1 minus sine almost looks like a 1 minus sine squared, because if I solve for sine cosine squared, so I would subtract sine squared. I'm just giving you a little heads up to think about what's about to happen. All right. So we have cosine squared is equal to 1 minus sine squared. And again, this is coming from the Pythagorean's identity, which you can see on two different slides. I think three different slides, or now, or two or three different slides. Two. All right. So our goal right now is that 1 minus sines down here. I want to turn him into a cosine squared, right? Try to simplify this as much as possible. And you'll see why. You'll see why. All right, so let's go ahead and continue on. So we're going to multiply the numerator and denominator by 1 plus sine u. So hopefully you heard this word called conjugate. Conjugate. We use it here and there in algebra. I don't use it religiously, but it does come up here and there in my college algebra courses where I talk about where we do the conjugate or the complex conjugate we were doing with imaginary numbers. So the conjugate, all it is the denominator. I'm going to multiply by 1 in the form of the denominator, which is 1 minus sine. But since it's called the conjugate, you change the sign from minus to plus. So again, this is an algebra move. So um, that's what they mentioned, in step 2 in that guideline. Use algebra, common factoring, or common denominators. So looks like we're gonna have to FOIL. So it looks like we're gonna have to FOIL. Do I have space? It looks like I have a blank slide. So expand the denominator. All right, I'm fine with that. All right. So let's go ahead and copy what we have here. So here we have cosine of u, cosine of u over. Excuse me. I know I didn't write the parentheses there, but let's go ahead and continue. We're going to multiply by the conjugate. The conjugate was the same thing on the denominator. Instead of a minus, we're going to turn into a plus. Now consider if this was one plus sign, the conjugate would be one minus sign instead. So it's always the opposite. It's always the opposite symbol. Whether it was plus, the conjugate is minus. If it was minus, the conjugate is plus. But let's get backtrack to our problem. It was one minus sign. So multiplying it against its conjugate is pretty much going to be a FOIL, right? It's going to pretty much be a FOIL. So for right now, it's going to be cosine u times 1 plus sine u. So let's go ahead and multiply that. But let's go ahead and leave them as is. And the reason I want to leave them as is, I want to factor him. I want to factor him. All right. Just so I can write a little bit smaller if I'm zoomed in. All right, perfect. All right. 1 plus sine u. All right. All I did is multiply by conjugate, and now I'm expanding. I'm expanding the denominator. All right. So now I need to FOIL. I need to FOIL here. All right. 1 times 1 is 1. Not so hard, right? And then what's nice about FOIL, we're gonna get we should get some terms canceled out. Here we have, what is this? Sorry, I skipped a gun. I'm foiling. All right, then we have 1 times sine. That's going to be positive sine u. I can use a different color. Then we have negative sine times 1. That's going to be negative sine u. Hopefully now you can see where what's going to cancel out. And then we have negative sine u times sine u, which gives me negative sine squared of u. So hopefully we can see that the signs cancel out, right? And we're left with cosine of u. Like I said, I wanted to leave them outside. I didn't want them to distribute it completely because we're going to have something wonderful happen. What's left over in the denominator is 1 minus sine squared of u. All right. Let's take a look. Earlier, what did I say that 1 minus sine squared is going to equal to? Once again, what are we using? The Pythagorean identity? Yes? So once again, we're using the Pythagorean identity right here. Once again. All right. So notice how I said, and even in chapter 5, even in chapter 6, this is the one that's real popular. It's going to come up a lot, and I even showed you how to come up with these other two. So you only really need to know this one because you can come up with the other two. You can derive them. And I showed you how to derive them as well. Okay. So coming back to our problem, 1 minus sine squared, 1 minus sine squared actually equals cosine squared, right? Cosine squared equals 1 minus sine squared. All right. So I'm going to make a new slide. And thank you for the heads up on how to delete this box. All right. So we're left with, I'm going to go ahead and change this to cosine squared, if that's okay. I'm going to do this, or at least I should fix this. No, wrong way. This one. I'm going to change that there. All right. So let's go ahead and continue. So here we have cosine of u, all multiplied to 1 plus sine u, all over cosine squared. Cosine squared. All right. Are we okay? Are we okay? I know these problems are a little bit more challenging because they involve a little bit of intuition. Of okay, this equals this, so I can substitute. It's always dealing about substituting and manipulating. So if we're good at manipulating people, hopefully we can use that skill to manipulate expressions. So cosine squared. The reason why it's cosine squared is um, again from Pythagorean's identity, sine squared plus cosine squared equals 1. Because before we were left with 1 minus sine squared. We were left with 1 minus sine squared. But Pythagorean's identity, right? Our boy, right? Our boy that we have Pythagorean theorem and now Pythagorean identity, Pythagorean theorem. All right. Says sine squared plus cosine squared. Always, I mean, I'm forgetting my, variable theta, right? Theta always equals 1. So actually, I can solve for cosine squared by subtracting sine squared on both sides. That's why I say that this one is yes, exactly. The next comment that came in because solving by manipulating the Pythagorean theorem, I get cosine squared is equal to 1 minus sine squared. So before I changed it, I had 1 minus sine squared of u. All right. But 1 minus sine squared theta, don't worry, I can change this to u. It's whatever variable you're respecting. If you're respecting u, then everybody has to be u. All right, perfect. So that's why we're turning this into that right there. Right. That's why I say bear with me with this chapter. Stop me anywhere. Stop me anywhere. That's why we can get lost real quick in this particular chapter because there's so much manipulation and substitution going on. All right. So you don't see this so much in calculus, depending on the institution that you go to. You go to here, at least at UTRGV, we don't have proof-based calculus classes. It's more computation. So at least we're seeing this in pre-cal. That's good. That's good. So you have a little taste of it if you do happen to go that route and go to one of those top big schools. All right. So I encourage everybody, to do their best, right, and to experience once this pandemic's over, experience one of those great universities. We're almost done. Almost done. We just got do a little manipulations first. Cancellation. So I know it might not seem obvious yet, but we can cancel a cosine and then the square because cosine squared isn't cosine squared just cosine times cosine, right? So cosine squared is actually cosine. I don't like to write it like this, right? It's a little bit elementary. Cosine of u times cosine of u actually equals cosine squared. All right. So what happens is one cancels out with the other, and then I think you see what's gonna be going on now. Hopefully you can see a little bit picture a little bit how we're gonna end up with secant plus tangent. So let me fix this a little bit. We have cosine squared, and again, cosine squared is cosine times cosine. So I can just cancel this square. I mean, this cosine. I know cosine squared is just cosine times cosine, so I don't need to worry about that square not there anymore. I'm not saying that this undoes a square. Remember, square roots is what undoes squares. So what we're left with 1 plus sine u is all over cosine. All right. Yeah, I know all the hints are they're assuming that it has small penmanship. So we did the Pythagorean identity. That's how we changed 1 minus sine squared to cosine squared, and then it says cancel common factor. Right now we did that. We canceled the cosines, and then it says next step separate into two fractions. So I do apologize. It's easier when you type it. When you write, I tend to write a little bit bigger, right? Just so we can visually all see it. All right, let's go ahead and separate what we have here, which is 1 plus sine u over cosine u, into two separate fractions. That was second to the last hint that we had. So we have 1 over cosine of u plus sine over u plus sine of u over cosine of u. Getting ahead of myself. And then I think you see, I want you to get your reciprocal identity, and I want you to help me out here. I want you to tell me what cosine of u is when the reciprocal identity. I want to write it as a trig expression that's not a fraction. So look at your reciprocal identity right now. Or I can scroll up. So we're looking at 1 over cosine and sine over cosine. So we're looking at 1 over cosine. Oh, I have that in red, don't I? Right. So I'm looking for 1 over cosine, and the other one was, I believe, sine over cosine, wasn't it? Does everybody see where I'm going with this now? Because I have 1 over cosine, I'm going to be able to use the reciprocal identity to rewrite that as secant. Ah, right, Eureka. That's why these problems are challenging, but at least when you're proving them, you know you're right or you're wrong because you don't arrive either to the left or to the right hand side. So that's what's unique about proofs. You didn't prove it if you didn't get to the other side, but that's what's challenging about proofs. And when you do study upper level mathematics, it's a lot of prove this. So it's proving pretty much mathematics. But this technique helps a lot when you're deriving equations. So those of you who go on to, again, engineering, mathematics, physics department, the deriving is very important as you're going to school, especially undergraduate. Again, you do so have technology on the field. You do have technology in the field, but in exam time, I think they're going to allow you with a laptop. So I think we're almost done wrapping the problem up. So 1 over cosine becomes secant of u. Sine over cosine, I know I repeated this more than once, is the ratio of sine over cosine is tangent. And I believe we have arrived to our right hand side. Interesting. How do you like me? I know it's a bit gruesome, because of everything is part of the answer. Like I had one student said, "Oh, okay, so secant plus tangent is the answer." I was like, "No, everything is the answer." So we did a little bit of work. We did a little work. That's why these are a little bit more challenging, like I mentioned at the beginning of the semester. So we started with the left hand side, right? Started with the left hand side, and and right here, this is what we're trying to prove. We started with the left hand side, and then at the end we ended with secant plus tangent, which we see that here. Secant plus tangent equals the right hand side. This is okay. Challenging in a sense that it may take some time. So like I said, I think I said it on Monday. Not too sure if I said it on Monday. Try to have this printed or on your phone, and this to help you while you're doing your homework. It's going to be very useful. Here we have another method. Let me see. All right. All right. We have a little bit of time left. What time does class end today? Think 10:45, right? 10:45. All right. We have a little bit of time, so we can finish this, and then I can put the homework for 7.1. I know those of you who already finished. Those of you who are up to date and already finished 6.5 and 6.6. I'm sure you're eager to get ahead, right? So you won't have nothing behind. So just a few slides. They mention here is another method for proving that an equation is an identity. All right. So we can transform each side of the equation separately by way of identities to arrive at the same result. Then the equation is an identity. So example 6 illustrates the procedure. Okay. So it wants us to verify the identity. So it says 1 plus cosine over cosine is equal to tangent squared over secant theta minus 1. So um, did I read that right? I feel like I read that wrong on slide 22. It says, if we can transform each side of the equation separately by way of the identity to arrive at the same result, then the equation is an identity. Okay, okay. Maybe you understood it when I read it, but when I read it, it just didn't register when I read it until I saw the example. So this example, and the literature they were trying to say about on proving particular identities, they say, okay, maybe you didn't get from the left hand side all the way to the right hand side, but let's say you were manipulating a particular side of the equation. Let's say the left hand side. We'll start with the left hand side, and obviously we see that on that slide. But if we can arrive at a certain expression, let's say we just get to cosine plus one, for example. And then we started with the left hand side, we were manipulating and we went up to cosine plus one. Then we start working with the right hand side. Then we start working with the right hand side. That should be deleted, right? Oh no, never mind. I'm speaking out loud to my brain, right? I'm talking and my brain wants to talk too. So we'll start with the left hand side. Try to arrive to a certain expression that's not exactly the right hand side, because if you think about it, both of them look complicated. Both of them look complicated. So this is a situation where we have two sides that look complicated because they both have fractions. So if I start with the left hand side and I can end up at a certain expression, which is not the right hand side, and if I start with the right hand side, and if I can arrive to the same expression, for example, the one I was saying, cosine plus one, then it's an identity. So that's one way you can do it without actually having proving the left hand side actually equals the right hand side all the way. And the same thing, right hand side, you don't have to show it going all the way to the left hand side. As long as you can arrive at the same expression, as long as you use legal moves in mathematics, right? You do all the algebra correctly. All right, so let's get cracking. Let's go ahead and try this out. It says verify the identity. So we'll prove this identity by changing each side separately into the same expression. Supply the reason for each step. So that's why these problems are a little bit challenging, especially on a paper exam, because you have to show every single step that you do on proving this. All right. So left hand side, let's go ahead and start with 1 plus cosine theta. Right. That's all they gave us over cosine theta. All right. Let me fix that theta up here. It's supposed to look like a pokeball, right? So here we have 1 plus cosine over cosine. So first things first, let's go ahead and break this fraction apart. All right, so that's just an algebra move. So we have 1 over cosine of plus, right? There's a plus, right? Respective was minus, you would do minus plus cosine theta over cosine theta. All right. To help me out with the reciprocal identities, what is 1 over cosine equal to? What trig identity do we have? What is 1 over cosine equal to? It's one of our trig identities. I know a secant, perfect. I'm great. I'm glad that you guys were able to answer that quickly. So secant of theta. And what do you know about cosine over cosine? That's going to equal 1. 1, right? So, all right, not much that we've done that, but now I'm going to go ahead and start working with the right-hand side of the equation. If I can arrive to secant plus 1, then I don't need to no longer continue my proving because I know they're both contained as secant plus 1. So that helps verify that these are a trigonometric identity without actually having to arrive to either side. So that's another technique we can have. If we can arrive at the same expression during our particular proof on both sides, then that is a legitimate trigonometric identity. So let's go ahead and start with the right-hand side. Right-hand side, we have tangent squared over secant minus 1. So let's go ahead and take a look at that. We have tangent squared theta over secant theta minus 1. Let me fix my Pokeball, my theta. Sorry, my theta. So my goal here is to try to get to secant plus 1, right? That's my goal here. Secant squared minus 1. Secant squared minus 1. I may need to refer back to my trig identity. Secant squared. All right. All right. All right. Let me go ahead and copy this. So yes, we're gonna have to be using one of the Pythagorean identities. I know the one that's circled in blue is the most popular one. So let's go ahead and copy this because we're gonna need that for our second half of our proof here. All right. So let me go ahead and paste this. I can erase some of this that doesn't pertain to our problem. All right. So here I have tangent squared over secant minus 1. So those are the ones that we mainly work with sines and cosines. Tangent obviously always going to come up. You know, it's part of the three main ones that we'll be studying. But for the most part, I feel everyone likes sines and cosines. The preference, you know, everybody has a different preference on how they view the world and how they see mathematics. So tangent may be very easy to work with. So here we're going to be working with another one of the Pythagorean's identities, not the main one, the juicy one that we always use. We're going to be using the second one, which I hope you can see the connection now, because I'm dealing with a tangent squared in my particular problem, which has a tangent squared over secant minus 1. And I need to, do something to help me cancel out terms to get a secant plus 1. Because if I look at my tangent squared, I see tangent squared plus 1 equals secant squared. So that's close to getting secant plus 1. It's close. It's close. Do you agree? Do you agree the one I'm about to write here? Circle? Do you agree that this might be a good candidate to use to rewrite tangent squared as something else? Obviously, I would have to manipulate the equation. So let's pull that one. Tangent squared plus 1 equals secant squared. All right, so here, too much. All right, we have tangent squared plus 1 equals secant squared. All right, so I want to get rid of that tangent squared. I want to get rid of that tangent squared, so I'm going to solve for tangent, right? So all I have to do is minus 1, and I have tangent squared, obviously of theta, right? Of theta is equal to secant theta squared minus 1. Do you see what I'm doing now? It's virtually the same thing, but I'm working with another one of Pythagoras' uh, identities. It's -1. So do you see what I'm gonna do now? I'm gonna change this for that. Does that make sense? This is Pythagoras' identity again. Pythagorean one of Pythagorean. Okay, perfect, perfect, perfect. So again, yeah, it helps to be familiar with these identities as well. I know they've been showing us since chapter 5 these identities. So moving on, where that's this allows us to rewrite tangent squared as secant squared theta -1. And the reason that I wanted to go with that, I know sometimes it's not obvious. The reason I went with that one because I saw there was a secant there, and I know for my previous part A of this proof, I ended up with a secant +1. So I wanted to work with one that had secants. All right. This one, unfortunately for the last one, that one had cotangents and cosecant. So that was a bad candidate. This was a bad candidate as well because there was no tangent squares and secant squares. So those were completely bad candidates. So that's why I went with the middle one, if you're wondering. So hopefully that clears some confusion. We're left with secant theta -1. -1. Now the top part is known as a difference of squares, because one squared is still one. Is still one. So this is actually an algebra move. I apologize. This is like the first thing I go over in college algebra. One of the first things I go over. Right here is a difference of squares. This is a difference. I know we don't have enough time to talk about difference of squares because that is something we learn in pre-algebra, but I also talk about it in algebra as well. I do a refresher every time in algebra. So the difference of squares tells us that we have a squared minus b squared. It equals a plus b times a minus b, right? So this is from algebra. This is from algebra. So again, I should write difference of squares up here on this step right here. This is difference, and that's the problem that I was talking about. That took me 30 minutes to finish proving something, which was only like 1 minute long. It was a difference of squares technique. So it gets us. We haven't seen something or played with something in a while. So technically, I have secant squared -1 squared because 1 squared is still 1. So technically, this satisfies uh, the condition for me allowed to use the formula for difference of squares. So next, this gives me. Let me write. It's not letting me write no more. Can you hear me? There we go. All right. All right. So the difference of squares allows us to write the top part, which is difference of squares. Is going to allow me to write this as secant theta -1 times secant theta +1. I know I wrote it backwards. It doesn't matter. It could be a minus b or a plus b. And it's all over secant theta -1. All right. So what do you notice? It looks like we can cancel out some terms. We get secant theta -1 to cancel out with the secant theta on the denominator. And then we're left with slide. And then we're left with we're left with secant theta plus 1. Now, the right-hand side was a little bit more trickier than the left-hand side because it involved using the Pythagorean identity and the difference of squares. The difference of squares. All right. So it follows. Since we're on the left-hand side, we're able to arrive at secant plus 1, and the right-hand side, we're able to arrive to secant plus 1. We do not need to continue further into proving this because we got the same thing on both sides of the proof. So it follows that the left-hand side equals the right-hand side. So the equation is an identity. So I want you to do your best when I upload the homework there. When it comes to the exam, I'll review. I won't try to trick you on what type of proof. Maybe I might have like a small set of proofs, and be prepared for one of them that may occur. So if it comes down to that, but we'll talk more about that as we get closer to the exam. Again, the next exam is after we finish chapter 7. So two more slides left. They say we conclude this section by describing the technique of trigonometric substitution, which we will use to convert algebraic expressions to trigonometric ones. This is often useful in calculus, for instance, in finding the area of a circle or an ellipse. One slide here. One more slide. We're almost done. It says a substitute sine theta for x. So they want us to put sine theta for x, right? For x. In the expression and simplify, assume that theta is between 0 and pi over 2. So we're in the first quadrant. We're in the first quadrant between 0 and pi over 2. So they're giving us some restriction on the angle. Because remember, we've simply been just taking sines and cosines, tangents, secants, cosecants, cotangents of angles. Pretty much this whole class. So they said setting x to be secant, we get the following. We get 1 minus x squared. 1 minus x squared is equal to, we're going to substitute sine theta for x. It's just substituting sine theta. Sine theta. All right, now they say Pythagorean identity. So if we haven't caught on yet, let me do it again for you guys. So here we have cosine squared of theta plus sine squared of theta is equal to 1. All right. I'm missing something because this x has a square, so there should be a square here on the side. Apologize. Right? Can't forget about the square. All right. Let's go ahead and just solve for cosine squared. We get 1 minus sine squared on both sides. Excuse my constraint of space. I'll change this to color so we can differentiate. And we're left with cosine squared theta is equal to 1 minus sine squared theta. All right, that's going to allow us to substitute 1 minus sine squared as cosine squared. We get square root cosine squared of theta. And then what's going to happen with the square root and the square, which gives us a hint there in the blue, is to take the square root. We're left with cosine of theta. I forgot my close parentheses there. And we are left with cosine. Cosine is positive in quadrant 1 and quadrant 4. Remember, we go counterclockwise. Quadrant 1, 2, 3. Fix that 3. And then 4. So cosine is positive in this one and in this one. And so what did they say? The last equality is true because cosine of theta is positive for the values in of theta in that question. So this wraps up 7.1. So a little tricky when it comes to proof, but these problems involve having to sit down and I mean I don't drink coffee myself, but those of you who drink something to give you energy, sit down, look at these problems, have your reciprocal identities, and I think you should have success for the most part. But if not, I'm always open for office hours, right? Morning, afternoons, evening if necessary. So let me know. I know we're 2 minutes after 10:45, but we are done for today. We finished 7.1. So I'll go ahead and have this homework ready up this afternoon. I have another course back to back, so I'll make sure to have 7.1 open for um, for you guys, so you can have time to work on it later on this afternoon and this evening and this ad as well as this weekend, or for Friday as well for homework day. Fridays are homework days, so that will give you good time to catch up on any homework you're behind, especially if you're behind cosines, sines, and now 7.1. So it's building. So don't fall behind. Procrastination gives us gray hairs. We don't want gray hairs, right? All right, we are done for 7.1. We will continue with 7.2 on Monday. 7.2. Um, don't know how long it is, but let's see. Oh, well, I would like to check, but we're out of time, so I don't want to hold anyone back. We are done.